All transmission lines, including optical fiber, exhibit some loss or attenuation of a transmitted signal. In fiber, much of the loss is intrinsic, that is due to the glass itself. However, external conditions, such as excessive bending, connectors, and splices also contribute to signal losses. The dB, or decibel, is a measure of signal gain or attenuation between the input and output as shown by this formula. dB equals 10 log of the output power, divided by the input power. Because it represents a ratio, the dB is a relative unit. Fiber attenuation is expressed as dB per kilometer. This graph shows the attenuation of a typical fiber plotted against wavelength from 700 to 1900 nanometers. By looking at the graph, it is easy to see that fiber is most transparent to a range of infrared wavelengths from 800 to 1600 nanometers. Wavelengths longer or shorter than this range are highly attenuated. Historically, early systems operated near 850 nanometers using multimode fiber with typical losses of 3.75 dB per kilometer. This is known as the first window because optical sources and detectors became available for this wavelength in the mid-1970s. Continued research and development paid off between 1980 and 1983 when devices became available that operated in the second window, near 1300 nanometers, where attenuation was reduced to 1.5 dB per kilometer. Early single-mode systems were also specified for use at 1300 nanometers, which provided attenuations near 0.5 dB per kilometer. In the late 1980s, when the first transoceanic links were installed, system wavelengths were specified at 1310 nanometers because the fiber's minimum dispersion point was closer to 1310 nanometers. In 1986, systems operating in the third window, near 1550 nanometers, appeared, and in the late 1990s, a fourth window, at 1625 nanometers, began to be exploited. Today's laser technology can produce highly stable devices over the entire range of low attenuation wavelength windows. The term window referred to a center wavelength as well as a range of wavelengths on either side. This general term has worked up through the late 1990s. However, optical amplifiers did not match up with the 1550 window, so the industry started using a new term called bands, analogous to the frequency bands of radio. The band concept groups ranges of wavelengths in a more defined and logical manner within the range of optical amplifiers used in single-mode systems. This chart shows a list of transmission windows as well as the bands used in fiber optic systems. Among the intrinsic optical losses present in fiber are absorption and scattering. Absorption is caused by impurities such as metal ions and hydroxyl ions introduced in the manufacturing process. The impurities absorb portions of light energy and re-emit it as minute quantities of heat. Scattering refers to light being deflected from its intended path. In fiber, some scattering is inherent to the fiber itself, called Rayleigh scattering, while other scattering is caused by fiber bends and manufacturing irregularities. All optical fiber contains minute random variations in the density and concentration of the glass material, having slightly different refractive indices. These variations are not impurities, but are frozen into the glass during its manufacture. When light rays encounter this patchwork of variations, they can be reflected in all directions, including back toward the light source. The portion reflected back to the source allows optical time domain reflectometers, or OTDRs, to estimate attenuation levels. There is another type of intrinsic fiber loss that typically results from impurities called a point discontinuity. Point discontinuities are usually byproducts of the fiber manufacturing process. Absorption and scattering losses in fiber can be highly wavelength dependent. Specific ranges of wavelengths tend to be absorbed by impurities in the glass. Scattering increases as wavelength gets shorter. This is why we see the characteristic dip in the fiber attenuation graph in the infrared region. It is also the reason that multimode fiber attenuation is lower at 1300 nanometers than at 850, and that single-mode attenuation is lower at 1550 than at 1310 nanometers. In addition, many older single-mode fibers have excess attenuation at 1385 nanometers due to absorption caused by residual hydroxyl ions in the glass, the so-called water peak. Recently, a new type of fiber became available referred to as low water peak fiber that virtually eliminates the attenuation peak near 1385 nanometers, opening this range for communications use. In this example, a 1400 nanometer source is used to demonstrate the flat response of a low water peak fiber. Some extrinsic sources of attenuation in optical fiber include macrobending and microbending losses. Macrobending loss shows up when fiber bend radius decreases. As the bend gets tighter, light rays within the fiber begin reflecting at angles allowing them to pass through the cladding and out of the fiber. The more the fiber is bent, the higher the attenuation. Bending losses are highly wavelength dependent. In this example, we see the attenuation resulting from the same amount of bending at 1310, 1550, and 1625 nanometers. Notice that the same bend at 1625 nanometers results in severe attenuation compared to 1310 nanometers. Microbending losses arise from stresses on the fiber caused by cable stranding, tight clamps, tie wraps, or rocks pressing against fiber cables. These external pressures cause minute deviations in the waveguide path as measured from the axis of the fiber, which results in higher attenuation. External microbending can sometimes look like point discontinuities on an OTDR.